Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics, Springer-Verlag, 2000. And today, this lecture is Chapter 7, Thermometers, Manipulations of the Partition Function. Today we're going to discuss how a thermometer works. We're also going to discuss equipartition theorems. And so we begin in the book with side B on page 90, How do thermometers work? The polythermal ensemble. The basic issue is as follows. An ensemble is a complete list of all of the states of the system, plus the statistical weight assigned to each state. Yes? Now suppose we take this room and we set up the canonical ensemble given that there's some temperature in the room. But suppose instead we manage to get the heating system a little higher and the temperature goes up. What happens to the ensemble? Well, all of the statistical weights change because we changed beta 1 over kT. What happens to the list of states? Nothing. The list of allowed states of the system is exactly the same at both temperature, namely, each gas atom can be anywhere in the room, and each gas atom can have any momentum at once. The probabilities and the relative probabilities of those states are the same in both ensembles. However, while the ensembles are the same, the states are the same, let me say that differently. The probabilities are different, but the lists of states are exactly identical. So now let us consider we come in with an ultra-high grade camera, better even than this one, and we take a photograph of the system, and the photograph shows the exact position of every atom, and it shows the exact momentum. Yes? Mm-hmm. And I ask you, what is the temperature in the room? Well, the response in some sense is you're using a thermometer somehow. A thermometer is a machine. It's evaluating some mechanical variable. And therefore you might think, well, I will go in and I can therefore calculate the temperature of the room, can't I? And the trivial answer is, well, no, obviously you can't. Because that photograph could have come from an ensemble at absolutely any temperature, and it would be the same photograph. Only if your camera were clever enough to record the statistical weight, which is not a mechanical variable, could you tell what the temperature in the room was. Nonetheless, people insist on buying thermometers and mounting them outside their houses. And all of these television stations hire whatever to stand there and look intelligent and tell people what the temperature was yesterday in case they haven't noticed. But if you ask, well, what did they just do? And so first we're going to give the orthodox statistical mechanics answer, and then I will show why it's wrong. And then we will give a version, one of the two versions of the correct answer. So the first version of the correct answer, or rather the not so correct answer, is we will go into the system and we will calculate the average energy. Well, we can't really calculate the average energy. We will calculate the energy of all of the gas molecules. And it's not an average, it's just a number. It's a fairly healthy number, but it's a number. And then we will say that the average energy is, for if it's point monoatomic gas atoms, which of course it isn't in this room since we can breathe it. But if we had a box that was an ideal atom, gas, point monoatomics, we could go in and we take the energy and we divide by 3/2 K sub B. And that gives us a number which has units of temperature. And if the gas were at that temperature, its average energy would be 3/2 K sub B times T. So what we do is we say, we will take equation 6.1 and we will divide out the N times 3/2 K sub B, and we get a temperature. But we will do this not for the average temperature energy, we will just do it for the energy we measure at one moment in time. Now you might worry, well, the energy in the room isn't always the same. It's allowed to fluctuate. We calculated that. In fact, in equation B.2, we calculate the RMS energy fluctuations, and it's 3n over 2 square root times kT. So there's an average energy, which is linear in n. There is a fluctuation in the energy, which goes as n to the 1/2. So far, so good.
Mm-hmm.
And now what we say is, well, we have this thing that is the fluctuation in energy. And so if I measure the energy, if I look at the system, I say, gee, I will take that equation, B.2, I will divide the square root of 3n over 2 K sub B to the other side of the equation, and I will have an equation for what is in fact delta T. That is, I will have delta E over some constants must be the fluctuation in the temperature. Yes?
Mm-hmm.
And so we will say we have an energy in the room, an average energy that's determined by the temperature. We have energy fluctuations in the room that is correctly given by equation B.2. And we will say that those fluctuations are in fact fluctuations in the temperature in the room. They're the size of the fluctuations in the temperature. And they grow as a square root of n. So that is what you will find in many statistical mechanics books, especially the ones written by physicists. Now we have, however, a little technical problem. If you think of how we derived equation B.2, we derived it within the canonical ensemble, right? And what do we know about the canonical ensemble? It has three constraints: the number of particles in the room, the volume of the system, and the temperature. So we calculated the temperature fluctuations in a system all of whose member states have the same temperature. This is absurd. It's also completely wrong. Every 10 or 20 years there will be an exchange of letters in something like Physics Today, where the people who understand the problem try to convince the people who are a little unclear on things that the assertion that there are temperature fluctuations is completely wrong. They're energy fluctuations. Okay, so that's the wrong answer and why it's wrong. This is not very complicated. However, it's not very complicated once you think about it from the correct point of view, namely equations B.1 and B.2 come from the canonical ensemble where the temperature is fixed, and therefore assuredly there can be no temperature fluctuations. However, the energy in different states of the system is not the same. So if you take equation B.1 and replace E average with the energy you measured once, and say, I can compute the temperature this way, something is wrong because you don't get the same value of the temperature each time. Mm-hmm. Okay, so how do we undo this issue? There is a magical phrase, Bayesian analysis, B-A-Y-S-E-S-I-A-N, Bayesian analysis. And the general problem of which this is an example is that you want to turn a process around. And instead of saying the temperature is X, what's the energy, we want to invert the process and ask the energy is X, what is the temperature?
Okay.
So that is what we're going to do. Now the problem with this is you can't do this in the canonical ensemble, because in the canonical ensemble there is one and only one value for the temperature.
Mm-hmm.
So what we do is to say, we are going to construct a slightly larger ensemble. So we need a bigger filing cabinet. And the slightly larger ensemble, we're going to take a subset of it in a bit, contains the canonical ensemble for the system, one copy for every value of the temperature. So there's an extra variable labeling the states of the system, it's T. Our system, well, our list of states of the system thus became larger by being multiplied by a continuous infinity, because we now have, it's exactly the same photograph, but it's one copy of the photograph for every temperature. Okay, so now we have something really big. Now I'm going to shrink it slightly. I'm out of this big set of all energies and temperatures. I am going to chop out the photographs, all of the photographs that show a specific value for the energy of the system. So there will be, the gas molecules in this box have an energy of exactly 100 joules, and this is the 3 Kelvin picture, and the 9 Kelvin picture, and the 18 Kelvin picture, etc. So we go in and we pull out all of the elements of the ensemble which have a specific value of the energy. And this is a big list because it is includes the same set of states and lots of different temperatures. So far, so good?
Mm-hmm.
This is the polythermal ensemble. The feature of the polythermal ensemble is that it includes all temperatures. Okay, now we have a little challenge. There are two ways to solve the challenge. There's the path I used in 1984 when I wrote a paper on this, and there is a more recent path. Because if we're going to say we have all of these states with all of these different temperatures, there's a question. How likely are two temperatures going to be? Suppose I have the same photograph and the sum of the statistical weights of all of the photographs is the same, or not. Are all temperatures equally likely or not? What I said in 1984, which is one of the two reasonable answers, is that every temperature is a priori as likely as every other temperature. I mean, if I just tell you here's a snapshot and I don't tell you what the energy is, there's no reason why it should be 19 Kelvin or 273 Kelvin or 3 times 10 to the 12 Kelvin. It's going to be something, but they're all equally likely. The other thing you can say, after all, a thermometer is an experiment of the first kind. Any typical thermometer has an error range which is some percentage of the temperature you measured. So if I can measure a temperature within 1 Kelvin at room temperature, that's respectable for a room thermostat. If I tell you the temperature of the liquid helium is 1 plus or minus 1 Kelvin, that's kind of worthless, but a thermostat that is doing that measurement that could work at both temperatures would have similar percentage errors, perhaps, at both of them. And therefore you say that the distribution is log normal, so that the probability of having a temperature between 1 and 10, or 10 and 100, or 100 and 1000, those three probabilities are equal. So that if I say we have a range of temperatures here, the a priori, the fractional range of temperatures is what gives us the temperature difference, or the probability of the temperature. So I have this little piece, and these are both alternative paths. Now what do? Well, I've said that all, in my paper, I said that all temperatures are equally likely. And so we have all of these states at each temperature. Each temperature separately is equally likely. So if I add up the total probability of all of the states at all temperatures, well, it won't be 1 because I didn't normalize it. But the probability of this state right here at this temperature is the statistical weight of this one state in the canonical ensemble divided by the total statistical weight of all of the states in all of the canonical ensembles. You may correctly worry, well, gee, if you add up all of those temperatures, is the total of all of the statistical weights a convergent integral? Because one answer is you keep adding up the statistical weight at higher temperatures, 1 billion degrees, 1 trillion degrees, 1 quadrillion degrees, and gross national product degrees. You add up, maybe it's national debt degrees, you add up all of these temperatures, the likelihood at all of these temperatures, and yes, the statistical weights up at quadrillion degrees get very tiny. But there are an awful lot of temperatures up near 1 quadrillion degrees. So who wins? The answer is the integral is convergent. And therefore you can go in and say we will add up all of the states at a given temperature and say what is, and we will have the probability of an energy given that temperature. You did that. We did that. It's the density of states problem. The total probability of all of the states with fixed energy is something we have already calculated. It is equation B-9 on page 94. Well, it is up to a normalization, which we should talk about. So we are going to actually do the calculation. Yes? And so, what do we say? Well, the first thing is we have a lot of gas molecules, and each of them has some individual energy. And we would like to add up over all of the combinations of energy that have the right total energy, and we will call the total energy we want E0. So what we say is we have molecule 1 and molecule 2 and molecule 3, and if you look at the second line of equation B-7, you see that molecule 1 has a probability of having energy E1 given that the temperature is T. Molecule 2 has a probability of having energy E2 given that the temperature is T, etc. And we are going to add up over all of the energies such that the total energy is E0. Well, how do we actually do that? How do we get the thing to add up? And the answer is, first, all possible energies might occur, so we do an integral 0 to infinity on the energy of atoms 1, 2, etc. through n. And then there's some, for a given combination, E1, E2, etc., there's some probability of getting that combination, which is P of E1, P of E2, etc. And then we stick in, last piece of B7, a Dirac delta function. Dirac delta function is a function that is 0 almost all the time, but it's really, really big if its argument is 0, and it's so big that if you integrate over it, you get a 1 out as the area under the curve. Now, how do you have a function that's 0 except at one point and has the integral over it be 1? Well, imagine a Gaussian. Take the limit that the Gaussian gets infinitely narrow and maintains its normalization. Gets narrower and narrower and narrower and taller and taller and taller. But its area is still unity because it's normalized. And if you take the limit that this function is very, very narrow and very, very tall, you get a delta function. And so equation B-7 is the probability of finding some energy E0 given that the total temperature is T. Well, that's fine. It's somewhat formal as an integral. The question is, how do you do the integral? And I shall briefly ask, have either of you ever seen the integral representation of the delta function?
I believe so.
Okay. Well, it's sitting right, it's equation B-8. B-8, there's this funny 2 pi that shows up, and it's an integral e to the I kx. Delta of x is integral e to the I kx dk over all k's. And that is actually a very useful trick. Because what we'll do is we'll take equation B-8 and we will stick it into equation B-7. We will also look up what is the probability of having some energy E given that the temperature is T. That's equation B-9. You've seen B-9 before. B-9, there is an x minus beta E, which is the statistical weight of a state of energy E. And there is everything else there, which is the number of states of energy E, properly normalized. So you combine all of those things and you get equation B-10, which is an Avogadro's number plus a couple of extra dimensional integrals. And the reasonable question is, what do you do with this thing? And the answer is, there is an integral dE raised to the capital N power. You do that integral and you get some function of k. And then there's an integral dk e to the minus ik E0. You do that integral and you get equation B-11. That's homework. So you make a note that you are supposed to get from equations B-7 through B-9 to equation B-11. Okay? Now, one thing you might worry about is, there's a trick. B-11, note the phrase, when properly normalized. That is, I did the steps from B-7 through B-9 to B-11. And then I calculated the sum of all of the probabilities and divided it through. So equation B-11 gives you a normalized probability for an energy at a given temperature. Or rather, for a temperature now at a given energy. That is, we took the original, here's the probability of an energy at some temperature. We added up the probability of the same temperature, same energy at all different temperatures. And we can now write down equation B-12, which is the probability of finding a temperature given the energy. So B-12 is the actual answer. It is a probability distribution for the temperature given you have an energy. And gee, what can you do with probability distributions? Well, you can calculate the first moment. That's equation B-15. Yes?
Mm-hmm.
And you can calculate the fluctuations in the temperature, which are equation B-16.
Mm-hmm.
Now look carefully at equation B-16. Look at the denominator. What happens to the denominator if capital N is equal to 2?
It blows up. It goes to 0.
The denominator goes to 0, and delta T blows up. Absolutely correct. That is, for a very small system. Oh, Well, the average temperature is okay unless n is equal to 0, but the temperature of a vacuum at this point is not a useful discussion point. But if the system gets small, the temperature fluctuations get large.
Mm-hmm.
And that is a matter that, yeah, there's not much of a probability of finding this energy if you're at a quadrillion degrees. But there are lots of temperatures up near a quadrillion degrees, and if you only have a couple of particles in the system, the likelihood that you will see that energy when you're at a quadrillion degrees is no longer negligible. It may be that what you would say are room temperature atoms, but there's some likelihood of finding them at some huge temperature, so the temperature is divergent. Curiously, if you, instead of calculating t squared and so on, if you calculate the moments of beta, beta is 1 over kT, it's the inverse temperature. If you calculate the moments of beta, this problem goes away. And so there's a fundamental sense in which beta is more natural than T is your temperature. That also shows up in the statistical weight x minus beta E. X minus beta E at small beta is well behaved. Exp energy over temperature, yes? What is the functional behavior of that as T goes to 0?
Blows up. It blows up.
Oh yes, it blows up. In fact, if you're taking the complex variables course, it's in a... Did I say something I shouldn't have?
We just came from our midterm.
It.
It's an essential singularity. Essential singularities are really nasty. And here is a demonstration of that. But beta is well behaved. So in a certain sense, beta is the more natural unit of temperature than T is. Don't expect your Weather Bureau to start reporting beta in the near future, though. Okay, so we have now done this. You can also calculate the relationship between T average and delta T that are calculated from the polythermal ensemble, and the T average and the delta T, the absurd delta T, that are calculated from the canonical ensemble. Yes? And if you do that, you will notice they're not the same. And so if you measure the energy of the system once, and it is a small system where these effects are significant, and you use equations B1 and B2 to say what the temperature is given that you have the energy, you will not really be getting the right answer. On the other hand, if you use the approach I described here, things will be better behaved. There is, however, a question. The other paper is by Prosper, it's footnote 2, of whether the distribution of temperatures should be linear or log spaced. That is, are there as many states between a quadrillion and 1 as there are between 1 and 2 degrees Kelvin? Or is it there are as many states between 1 and 2 Kelvin as there are between a quadrillion and 2 quadrillion Kelvin? Well, that's an interesting question where I do not have an actual resolution, but several people have looked at the question. Last question. Why does the temperature fluctuation blow up for small systems? And the answer, in a sense, is that if you go out to very high temperatures, there is a very small likelihood of finding the system in the state you're looking at. And so if you go out from room temperature to really huge temperatures, the probability that these two molecules right here have the same energy gets smaller and smaller. But there are a huge number of temperatures out there, and that makes more than makes up for it, and therefore it is most likely that this snapshot of two molecules was found in a state of some very high temperature. Okay, well, I gave you something to do, and it could also be said to be homework problem 4, confirm B12 and B11 from B7 through B10. Okay, that's it for how thermometers work. You should not worry that anything we've said greatly disturbs the operation of normal thermometers. There's nothing very wrong with the discussion, but there's some details which you think about carefully are not right. And now we will shove ahead to Lecture 7. Lecture 7 is formal manipulations of the partition function. Now, once upon a time, Lecture 7 was much more important than it is now, because Lecture 7 is all you did in statistical mechanics. You computed the partition function, and you took various derivatives, or logarithms, or other things, and by doing this, you extracted the free energy, the specific heat, and so on. This is actually still of substantial engineering importance. Suppose you are, for example, designing a rocket nozzle, where you're trying to handle gas at some very high temperature, and you would really like to know the specific heat of the gas. Well, you could try measuring the specific heat directly, but measuring the specific heat of a white-hot object is extremely difficult, because the heat tends to leak out of the device you're using without your planning on it. For gases, this is not so true for solids. For gases, it may very well be the best way to get the specific heat is not to measure it, it is to compute it. And if you have good information on the molecular spectra and chemical composition of your gas, your calculations will be much more accurate than any experiment is likely to be. So we start off, and we will start off with the equipartition theorem. The equipartition theorem is the lead part of this. It's the part that was known for a long time. And it starts with something we've already done, namely if we have a gas atom in a box, the contribution of one of the momentum modes, say P1x squared over 2m, the contribution of that to this total energy is the average energy. It is kT over 2, right?
Mm-hmm.
Yes, I was hoping I would get a response. Never mind. And if we have n of these contribution to the total energy is 3/2 nkt over 2. Mm-hmm. The contributions to the specific heat follow, namely one atom contributes 3/2 k sub b to the specific heat. N atoms contribute 3/2 nk sub b to the specific heat. The specific heat is simply dE average dt. So, that's what momentum does. The point of the equipartition theorem is the fact that we happen to be talking about momentum in equations 7.1 and 7.2. The fact that we are talking about momentum is not central. It could be some other variable. Which other variable? Well, that's why we have an equipartition theorem. And what we do, the equipartition theorem refers to systems whose energy has a particular form. Namely, there is a term we are interested in, which is 1/2 aq squared, and there is everything else in the energy. And the everything else can be anything you want that gives convergent integrals, except the everything else cannot include the variable q1 at all. the dependence of the energy on Q1 must be 1/2 A Q1 squared. Okay, well, let's calculate the contribution of 1/2 A Q1 squared to the average energy. It's an ensemble average, yes? In particular, it is the ensemble average of equation 7.5. You're taking the ensemble average of 1/2 A Q1 squared. So, what's in the ensemble average? There's a sum over all of the states of the system. In the numerator, there's the thing being averaged. And there's e to the minus beta energy of the system. That's the statistical weight. Now, I have already done one radical thing, and it contains a trick that is actually not obvious. The one radical thing I've done is saying, instead of writing the integrals dx, dpx, I'm going to call all of the variables q. That's what Gibbs did. And there are going to be 2n of them. And each, so for each, and why pairs? Because there's a position coordinate, and there's the canonically conjugate. We'll get to what that means in a moment. Momentum coordinate. So all variables show up twice. Once as the position, once as the corresponding momentum. And we add up over all of these variables, and I don't have to say what the bounds on the variables are, except that none of the bounds inside can depend on Q1. Yes? Okay. Well, the exponential of the sum is the sum of the integrals. Integrals whose variables, whose kernels, things being integrated over, can be separated out, can be factored. So we can take these integrals and we can factor them out. Yes? And so we end up with, so most of the integrals are the same in the numerator and denominator and cancel, and we are left with an integral over the variable q1, and all of the rest of the pairs of integrals above and below have canceled, and we have an integral dq1, 1/2 A Q1 squared, that's the Q1 contribution to the energy, times the statistical weight, but only the part of the statistical weight that depends on Q1 shows up. Those are one-dimensional integrals, aren't they? You can do them. In fact, you have done them replacing Q1 with P. And having done them, you get equation 7.7. The contribution of the degree of freedom to the average energy is 1/2 K sub B. And if you take d dt of that, the contribution of that 1 degree of freedom to the specific heat is 1/2 K sub B. Now this already gave Gibbs a very serious problem. Here is our trustworthy atom again. If it's a point, it's still, the energy still depends on the 3 momentum coordinates, and therefore the energy of a monoatomic gas should be 3/2 K sub B. Well, that's actually true, pretty nearly. If, however, I have a diatomic molecule, here's a diatomic molecule, it's an extended object. Because it's an extended object, it can certainly rotate 1, 2, and presumably 3. Furthermore, if it's flexible, which could be the case, the ends could stretch back and forth with respect to each other as though they were linked by springs. That's now 3 translations, 3 rotations, and G, 2 terms in the energy corresponding to the spring. So there are 8 terms for a diatomic. Each contributes 1/2 K sub B to the specific heat. So you predict this diatomic has a specific heat of 4 K sub B. One little problem with that. It's wrong. Gibbs ignored molecular vibration, so he said an ideal diatomic gas would have an energy of 6/2 K sub B. In fact, it barely makes it up to 5/2. It's a serious problem. The theory does not predict the simplest possible sort of consequence. And he was very worried about that, but he did not find a solution. We now know that the solution is quantum mechanics. The energy of the diatomic is very much less than is being proposed. Okay, so, however, we still have the equipartition theorem, and it tells you how much energy a single degree of freedom contributes to the average energy. It has, however, one minor difficulty. So we have the equipartition theorem. There are things where the energy doesn't look like this. Also, if you apply it to air, it should be pretty simple, you get the wrong answer. You get a wrong answer for the specific heat. Note, however, incidentally, that Gibbs thought the specific heat should be 6/2 K sub B. More modern calculations kind of yield 5/2 K sub B because they contain mistakes of a sort. Okay, so that's where we are. That's the equipartition theorem. Now we hit the first difficulty. There are systems whose energy is not quadratic and the variable controlling it. And we ask the question, is there anything at all we can do about this other than choose another homework problem and pretend you did the right one and hope no one notices? Well, the first answer is the generalized equipartition theorem. The first generalized, there are actually two of these. The first generalized equipartition theorem is due to Tolman, and it talks about the average energy. The second generalized equipartition theorem, guess what, talks about energy fluctuations, and it is due to me. So let us look at the first generalized equipartition theorem. And it actually starts not by calculating an average. It starts with the Q, the partition function. And what is proposed is we will take Q and we will do on it an integration by parts. The integration by parts shown in 7-14. That is, we'll take d of qx minus beta e and we'll replace it with components when it's the differential. So we do that, and having done that, we get equation 7-15. However, equation 7-15, there's an integration by parts. There must be a surface term or something analogous to a surface term. And it is the first term in equation 7-15. Yes, it's a surface term. But what we say for that term is, it's evaluated at the surface. There's always silver foil, well, tin foil. There's something at the surface. In particular, well, there is something in particular at the surface. The energy of the system goes to infinity at the surfaces of the momentum coordinates. And if the energy of the system goes to infinity, as is shown in 7-16 when we do the integral, if the energy goes to infinity, the statistical weight goes to 0. Furthermore, even if the energy of the system doesn't go to infinity at that limit, it might be the case that the limit is q equals 0, in which case qx minus beta e is 0, because q happens to be 0. Now, these conditions are actually quite commonly found. For example, they're found for harmonic oscillators, anharmonic oscillators, mass points, kinetic energy, and so forth. So we have equation 7-16, and if you look hard at 7-16, you'll notice the right-hand side is an exact differential, and we can take 7-16 and we can plug it into 7-15 and do a little work, and we eventually end up with 7-17. Now you might ask, if 7-15 has two terms, and we stick into 7-15 the integration by parts, why doesn't the number of terms increase? And the answer is that one of the terms from the integration by parts is 0. And the other one gives us this interesting result of 7-17. But if you ask, what is 7-17? Well, it's some integral over all of the coordinates, a function and divided by capital Q. That is a functional form you've seen before. What is it?
It's the average energy.
Well, it is the average. Q dE dQ may not be the energy, but it's the average of Q dE dQ.
Mm-hmm.
Yes? Mm-hmm. And it's going to turn out, if the energy is P squared over 2m, it is the average energy, well, twice the average energy.
Mm-hmm.
However, in general, we get to equation 7-18, which is the ensemble average of Q partial of E with respect to Q, is KT.
Mm-hmm.
Yes? Mm-hmm. Okay. And if you have a system which is has a more complicated energy, like 7-19, and stick that into 7-18, well, you get the results you see in 720 and 721. So, and one of those results really is the average energy due to that variable. So you were right for this system. You can repeat the calculation, do another integration by parts, and you end up with equation 7-24. And 7-24 shows what the equipartition theorem is going to do effectively. However, having said we're going to do another integration by parts, you can do it, and if you do it, you eventually end up with, gee, what do you end up with? How about equation 7-27? You end up with the second equipartition theorem, and there is a result, and we go through, and there's another result. There is, however, one little detail I've skipped. We're writing the sum over all the states. We're using Gibbs notation that the variables go Q1, Q2, etc. out to Q2n.
Mm-hmm.
Okay. Did we make a mistake? Did we leave something out? Well, we write the integrals as dq1, dq2, dqn, but suppose I just converted to spherical polar coordinates. I would pick up, not as part of the kernel of the integral, but in the variables, I would pick up, what would I pick up? I would pick up an r square sine theta, right?
Mm-hmm.
Mm-hmm.
Or if I was doing this to momentum coordinates, I'd pick up a p square sine theta.
Mm-hmm.
That extra bit says that the size of a differential volume depends on position. Yes?
Mm-hmm.
And what is it? It's the Jacobian of the transformation. Did either of you see Jacobians in calculus?
Mm-hmm.
Okay, well, we are looking at the Jacobian of it's something you have been doing intuitively all along, namely if I go to spherical polar coordinates.
Oh, it's the extra
r,
term. Okay.
It's the r
Yep.
square sine theta.
Yep, okay.
Well, there's a trick. If I am doing the list of variables, I have a set of n position variables, and then I must have a set of n momentum variables. If the momentum variables are the variables that are canonically conjugate to the positions in the Hamiltonian mechanics sense, guess what? This huge Jacobian is
1.
1. And we will actually show this in a later lecture. It's an important result. Then we get to the last thing, except I'm about to run out of time. And the last thing we do is to look at in 7.5 at alternatives for doing the ensemble average. And what I do is to say we have an ensemble average, and we can do parametric derivatives of the ensemble average. Or we can take the partition function or its log, and we can do derivatives of the partition function with respect to the volume V, the temperature T, and so forth. And I, in fact, in 7.5, go in and I will say we will take the average energy can be written as minus dd beta log Q. That's the two equations above it. And we will do another integration, we will do another derivative, and guess what? We get out, with some rearrangement, we get out dE dt, the derivative of the energy with respect to temperature, which is the specific heat. Well, there are a lot of ways of writing it, but the one peculiar one, or interesting one, is 7-48. Because in 7-48, I show that the specific heat is determined by, or determines, the mean square energy fluctuations. Okay? Your homework is to derive, or piece of homework is to derive 7-48 from 7-40, let's say 7-42, except the next two steps are not in the obvious time order. Okay? So you're going to derive 748, and I give you all of the words you need to say about the proof. You get to do the calculation. Finally, and this is a math exercise, I want you to start at equation 7-22 and derive equation 7-24. Hint. There is a constant c missing in the intervening equation. What you're going to do is integrate by parts twice, and be careful, and you will get there.
Okay.
Yes. Now, one bit on being careful is the last piece of 7-24, partial of QA with respect to QB. That's a term that's 0 unless A equals B. If you're doing an integration by parts on Q twice, it could be the same variable twice, or it could be two different variables. Are you good with this? Mm-hmm. We're done. Class dismissed.